Well, hey there, chemistry team. Let's get into solids in some detail. So we did a video introducing types of solids. We looked at ionic solids, molecular solids, and atomic solids, all based on the particles that make them up, and generally looked at the intermolecular forces, and we can kind of rank their melting points, or sorts of things like that, solubilities. But let's jump into the detail. So I said I was going to do a video separately on ionic solids. That's this one. And I was going to do one separately on network covalent solids that fall under the atomic solid category, as well as metallic solids. So we've still got quite a ways to go. We're going to dig into the gory details, but I wanted to start with ionic solids. So we covered phase diagrams, so we got all that all done in the last video. So let's look specifically at ionic solids today, which we've covered quite a bit, so I'm not going to review things we've looked at before. Let's dig into some more detail. They're the easiest ones to comprehend, at least for me, right? I don't know about you guys. Everybody's different, right? But ionic solids make a lot of sense. So you've seen these before, right? I'm not going to draw it on the board. But if you've got, say, the red is cations and the gray is anions, doesn't matter how you want to define it. This could be like sodium chloride or anything like that. So you form this array, three-dimensional array of alternating cations and anions. This happens to be in a 1-to-1 mole ratio. So +1 -1, +2 -2. But you get this, we call it a lattice, Lattice. So that's this lattice of the solid. What I want to look at is the energetics of this. So obviously, what would the energy be in forming this? Oh, okay, we call that the lattice energy. Hey. And so it's a great representation of the strength of the bonding forces. And we're going to be able to relate lattice energies to things like solubilities, melting points, et cetera, et cetera. It gives us a nice quantitative number, right, outside of Coulomb's law. So lattice energy, we're going to define that, and then we're going to look at ways we could actually calculate lattice energy. So we could compare two different ionic solids and say, which has the stronger ionic forces or the greater lattice energy. We're going to find out they're exothermic, so the more negative lattice energy. So let's, and again, it represents the strength of these bonding forces, but lattice energy by definition, think of it more in a thermodynamic sense, is defined as the energy change that occurs when you're forming exactly 1 mole of that particular ionic solid. But this is not like standard enthalpies of formation. You're not doing it from the elements in their standard states. You're doing it from the ions in the gas phase. So if you have the cation in the gas phase and the anion in the gas phase with the proper coefficients to form exactly 1 mole of that particular ionic solid, that energy change for that process is called the lattice energy. Not easy to do in lab, to get these ions in the gas phase and then do that. So experimentally, not so nice, but theoretically, it's great. All right, so we're gonna do some calculations, some diagrams with this. But remember, it's exactly 1 mole, so you have to have a coefficient of 1 here. All right, which means, like for this example, silver, so the silver oxide, since we have 2 silvers here because it's +1 and 1 oxygen anion, we need a 1 in front of that and a 2 in front of that, right? All right, let's make this happen. Let's take a look at how lattice energy relates to melting points and solubilities first, and then we'll get into how we can solve for this thing called lattice energy using the Born-Haber cycle. Ooh, once you get it's kind of like a game. Once you get how to play the game, these are tedious, but actually kind of fun in a nerdy sort of way. All right, let's take a look at lattice energy and how that would impact all these properties, which is the focus of this entire section that we're looking at, liquid and solid properties. So lattice energy values, think about it, right? Always when you're talking thermodynamics, always think, well, would that require energy and be endothermic, right? Like breaking bonds, boiling a substance, melting a substance. That would require energy because you're disrupting, breaking a bond or disrupting intermolecular forces, right? Or would that process be exothermic, forming a bond, right? Freezing something. So let's take a look at what lattice energy is. So lattice energy is taking cations and anions, happens to be in the gas phase, and bringing them together, happy, positive and negative, woo, and forming a solid. So don't you think if you take something that's so if you were a positive cation in the gas phase and you saw a negative anion in the gas phase, wouldn't you want to get to meet them? Woohoo, right? So that's a favorable process. So they're going to be exothermic, which means lattice energies are always going to be negative for compounds that you will naturally see, right? I guess we could make theoretical compounds, ionic compounds that wouldn't exist, like NaCl3. You know, what the heck is that? We know it's NaCl. That's going to be an exothermic, very favorable process. But NaCl3, that's not normal, right? So that may not have a negative value, right? But for this is for common ionic solids that you would see on a daily basis, right? They're going to be very large. I've seen them negative 2,000 kilojoules per mole, negative 8,000, negative 10,000 kilojoules per mole. I mean, these are some really big negative numbers. So now let's think about when we want to relate this to properties like melting points and solubilities in water. Let's reverse that process, right? Lattice energy is forming the solid. So the reverse process of the lattice energy, you're taking the solid, 1 mole of the ionic solid, and forming the ions in the gas phase, maintaining balance. So that would be splitting the ions, which would somewhat be, it's not melting per se, but it would relate to melting. It's not dissolving it in water per se, but it would relate to it, right? Wouldn't you think that the larger that negative value is, if you reverse it, the larger the positive value, it'd be more endothermic and it would require more energy. So typically you can relate lattice energies to you could calculate a melting point or solubility, but you could kind of qualitatively go, well, the more negative, the higher the negative value of the lattice energy, the harder it would be to separate those ions, which would mean that would probably relate to a higher melting point, right? The more exothermic the lattice energy. And since it's harder to separate the ions, it'd be harder to dissolve that in water, right? So the more negative the value of the lattice energy, negative 10,000 kilojoules per mole versus negative 5,000, would make it a higher melting point and less soluble in water. Make sense? All right. So now that we got lattice energy under our belt, let's take a look at how we can calculate it. Hard to do in lab because you got those ions in the gas phase. But remember from thermodynamics, there's a way to determine the enthalpy values for reactions, even if you can't do them directly. You can do them indirectly through the back door, because remember, if I'm here and I want to get to here, I can calculate that energy. But if I'm here and I go, whee, if it's a state function, I can get here as well. The difference between the initial and final state's the same regardless of what pathway I take. Hess's law. I highly recommend you review the video on Hess's law before you jaunter into the Born-Haber cycle we are about to do. Are you ready to jaunter into Hess's law, my friends? So the Born, this is hardly anybody calls it this, the Born-Haber cycle, which is a mouthful, right? So everybody I know just calls it the Born-Haber cycle. And we're going to do Born-Haber diagrams in a little bit. We'll do an example maybe in a separate video. So this is how we're going to go through the back door and figure out what lattice energies are, what they're mostly used for. So if we want to indirectly calculate the lattice energy, because maybe we can't do it directly in a laboratory or something like that, we're going to use Hess's law. Because remember, if there's two pathways to form something and it's a state property, the values for the two pathways should equal each other, right? You should get the same answer regardless of what pathway you take. It's path independent. Yay! So review the video on Hess's law. Okay, we're going to use Hess's law back in first semester of general chemistry under thermochemistry towards the end. And we're going to estimate values for the lattice energy. Ready? So this takes advantage of the fundamental aspect of Born-Haber cycles and Born-Haber diagrams, because these are key problems for this kind of stuff. You have to understand the basics of how we form these ionic solids two different ways. One, like we said, lattice energy, right? Forming the ionic solid, exactly 1 mole from its ions in the gas phase. And review from thermochemistry, from first semester general chemistry, standard enthalpies of formation. Remember that delta H sub F? And you can use thermodynamic tables to calculate that. We're not going to calculate in this class, but you have to know how to look up these values. Let's review this. Let's do the silver oxide as an example, like we've been doing. So let's get that brown pen here. So again, we already did this one for the lattice energy. We want to form 1 mole of silver oxide. Silver's a +1, oxide's a -2, so we need 2 silvers for every 1 oxide. We have to have a coefficient of 1 there, like we did. So silver's a +1, so we're going to go Ag plus gas. Oxide's a -2, O2 minus gas. And then let's get the coefficients right. We need a 2 for the silver and a 1 for the oxide. So that energy for that process is the lattice energy. So we can form 1 mole of the silver oxide solid from the ions in the gas phase, maintaining balance. You always got to maintain balance through. That's one way to do that. Another way is from the elements in their standard states. So let's say we want to form 1 mole of silver oxide, the ionic solid. But in this case, if we're going to use standard enthalpies of formation, remember the thermodynamic tables? Let's see if I have it. So from the thermodynamic tables, remember standard enthalpies. We're not doing Gibbs energy and entropy yet, but the standard enthalpies of formation, right? So you can take I think it's the coefficient from the balanced equation. Well, let's do the equation first, then I'll show you how you can do that. All right, so silver is a metal in its standard state, and it's monatomic, right? So we're going to take silver metal in the solid state, and then we'll have to balance this too. And oxygen's a diatomic gas in the standard state at room temperature, right? 1 bar pressure. So that's going to be O2 gas. So those are the elements in the standard states. Now let's figure out the coefficients. So we need 2 silvers, because we have to have a coefficient of 1. So just like we did before. But look at that. We need 1 oxygen anion, 1 oxide ion. But we have a diatomic element there, right? So what coefficient do we need there? What times 2 gives you 1? Oh, 1/2. Oh no, cheerio. Normally we don't like fractional coefficients, but a lot of times in thermodynamics, when you define the product as exactly 1 mole, a lot of times you're going to end up with 1/2 and 3/2 and things like that in your coefficients on your reactant side. So would you agree with me? Here's 2 completely different ways to form exactly 1 mole of any ionic solid, right? In this case, it's going to be silver oxide. So we're going to use the advantage of this to say, hey, there's 2 ways to get to this. I'm going to draw this really cool, it's almost like a logic game, where I'm going to get to it. I'm going to start with the elements in their standard states, get to it here, and then I'm going to take those elements to their standard states, get them to the ions in the gas phase, and then get to that. So I can take this pathway, or I can go up and over, and then we can calculate lattice energies from that. Let me show you how to set this up. Okay, follow along with me. Let's do the easier way, Born-Haber cycle. Let's do it for a generic ionic solid. So the way you're going to set this up, and we're going to look at diagrams in a little bit. What we want is 1 mole of the ionic solid on the bottom of your page. Right? Whatever that ionic solid is. So put that on the bottom, and then we're going to form it 2 different ways. So we're going to do it from the ions in their gas phase, right? So let's put the ions. How do you spell ions wrong? In the gas phase. So let's say we have the ions in the gas phase. Well, if I went from the ions in the gas phase down to the solid, wouldn't that be the lattice energy? Right, by definition, whatever the solid is. Okay. I'm going to move this over just a little bit so we can get that arrow all the way to the bottom there. Boom! Little energy diagram there. And we can also form the ionic solid from the elements in their standard states. Right? So let's put this over on the other side. So let's put elements in the standard state. Oops, I spelled that wrong too. I'm on a roll. That's going to be a little bit less than the lattice energy. Lattice energy is huge. But couldn't we go from the elements in the standard state to the ion, right, the ionic solid, and that is your delta H naught formation. So you see how we can get there 2 different ways? It's like chutes and ladders, right? You ever play that? Like, woo! I got 4 kids, so we played a lot of chutes and ladders. I loved it as a kid too, but you always get to the top and take that one lung ladder. You're like, I'm about to win. No! And you take that chute all the way down. You're like, whatever. All right, here we go. Let's call this path 1. Let's call that pathway 1. If we say this is our starting point, all right, you're in, get the engines running, boom, 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 and you could go, boop, right? Take the ladder down, bang, I'm there in one step, woo, woo, I like it. And we can just look that up in the thermodynamic tables. Good to go, right? Or I could choose to go all the way around. So instead of taking the easy path, let's take the harder path and say, well, could you take the elements in the standard states, convert them to the ions in the gas phase, and then go all the way down? That's a lot harder path, but isn't that true though, right? So let's call this path 2. From Hess's law, shouldn't path 1 equal path 2? If this is truly a state function, let's go like this. Now, path 2 includes the lattice energy, right? Path 1 includes the standard enthalpies of formation. Okay, so if path 1 equals path 2, there's Hess's law. All right, now, obviously, we got to put the equations to it, the numbers to it, and from that, we can solve for actually any part of this whole path we can solve for. But if we know every part of this pathway, which we're going to have to figure out in the next board, we could solve for the lattice energy. It's very commonly used that way. But that's a really generic way of looking at the Born-Haber cycle, right? Start here with the elements in their standard states. I'll put start here. Start. All right, that's your starting blocks. And you could just go boop in one step there, or hard to climb up, but it's a longer way down. It's like when you're, sledding or something. We just went to Big Bear to go sledding. You can take the little small hill and just go, wee, it's not that exciting, but you might climb there was a guy that was there. He would just go up to the craziest top. He'd trudge. I'm like, man, you got to be exhausted. He'd go, all the way, he's cold, he's falling. And then he's like, yeah, baby, all the way down. Right? It's a little more fun that way, a little more dangerous. So I don't care which path you take, but the overall energy is just from here to here, right? At the end, right? Because you got some going up and some going down. Let's take a look at specifically for, we'll do generic first and then we'll do silver oxide. All right, let's look at the two pathways in detail here, right? So for the Born-Haber cycle, we want to form the solid, right? The ionic solid. So we can do that in path 1. That was that one step from the elements in their standard states. Boom. And that's your standard heat of formation, which you can get from thermodynamic tables, right? So you can look that one up directly. We can also solve for it, but typically we're going to look that one up. And I'll give you those values. I'll probably give you a thermodynamic table. Step 2, remember that's the long one. Step 1, boop. Step 2, all the way up to the ions in their gas phase and then combine them using lattice energy. So how do we get the elements in their standard states? We're taking the elements in their standard states, converting them to the ions in the gas phase, and then we can combine those via the lattice energy to form the solid. So that's path 2. Path 2 is a lot longer than path 1 because path 1 is always one step. So path 2 can be 4 or 5 steps. So I put all 5, but it turns out step 3, I'll put a little star next to one. That one may or may not be necessary. So let's walk through it. This will be a lot easier later when we do a Born-Haber diagram. So anyway, I just want you to understand the process of Hess's law. So step 1, we're going to take any elements that are not in the gas phase, for example, the silver, and we got to get it into the gas phase because we're trying to get the ions in the gas phase. So if you've got a solid, you need to sublime it with the molar heat of sublimation or molar enthalpy of sublimation. If you've got a liquid like mercury or bromine, you're going to have to use the molar enthalpy of vaporization. So like here for the oxygen, that's already a gas, so we don't have to worry about it. But the silver is a solid, so the first thing we need to do is sublime 2 moles of silver to 2 moles of silver in the gas phase. And we'd have to look up the molar heat of sublimation, which I would provide for you, or if you're doing homework, you can look that up in a textbook or a table or something like that. All right, easy. I got all my metal. I got my metal and my non-metal in the gas phase now. Yay. Step 2. You don't have to you can do the non-metal first or the metal. I just like to do the metal first. I got to get that metal and convert it into a cation, right? So for example, for silver, we would need to get that into the +1, meaning we'd need to remove electrons. Well, convert the metal to the cation. That's the ionization energy from last semester, right? So if you want to review that video from last semester on ionization energy, that might be helpful, all right? And you can look up those values. I will provide you a table of ionization energy values. Yaha, right? This isn't complete, but you just find it. And some of them might have multiple charges. So if we were doing, maybe magnesium, see I1 and I2, remember first and second? So if it's magnesium, there's going to be two things here, going from magnesium in the gas phase to magnesium +1, and then magnesium +1 to +2. You have to do that in two distinct steps. But in this case, silver would just be a +1, so that would just be the first ionization energy from the silver in the gas phase to boop, silver +1 in the gas phase. Then we got the metal cation in the gas phase. We're good to go. And watch out for the coefficient. In this case, we'd have to multiply that by 2 because we got 2 moles of it. All right, so once we got the metal taken care of and we've got it into its proper charge, then we can look at the nonmetal. If the nonmetal is diatomic like oxygen, right, it's not in the solid. O2 minus is not diatomic, it's a monatomic. So we have to break that OO double bond, okay? And that requires bond energy, also from last semester. So all the diatomics, chlorine, fluorine, bromine, oxygen, nitrogen, hydrogen, all those babies, the Magnificent Seven, need to be broken apart. And that is your bond energy. So I would provide you a bond energy table. So in this case, we'd have to break the oxygen-oxygen double bond, which would be 498 kilojoules per mole. We only have half a mole, so it would be half of that, right? And once we do that, we would end up with one oxygen atom in the gas phase. We need that as an anion, though, right? So if your nonmetal is not diatomic, you can skip step 3. Whoop, whoop, right? Hey, good deal. But most of the time, we're going to have to break that diatomic molecule, okay? Step 4, once we have our nonmetal as a monatomic species in the gas phase, then we've got to convert it to the anion, which means we have to add electrons to it. We'll do the equations on the next board. I'll show you how they add together via Hess's law to give us this. We're going to add all these steps together to get that, right? Then they should equal each other, right? So in order to add electrons to something to form the anion, that's called the electron affinity. So I would give you a table of electron affinity values, right? And you can see for oxygen, there's a first and second electron affinity. So we would have to do that in 2 steps. We'd have to take the O gas, turn it to O minus gas by adding an electron, and then to O2 minus gas in 2 steps. If it's a -1 charge, like chloride or bromide, any of the halides, it's just a 1 step. If it's nitride with a -3, you have to do it in 3 distinct steps, right? But you can do that, and if you want to go review electron affinity and ionization energies from last semester, that would be helpful. Last but not least, we will now have the nonmetal in the gas phase with the proper anion charge. We've got the metal in the gas phase with the proper cation charge. We just combine them, boop, to form the solid. Combine the gaseous anions and cations, and that's your lattice energy. Add these all together. Path 1 should equal path 2. Let's do some equations on the next board. A little review from last semester for you in case you're a little rusty in the brain. You ready for some fun? This is the hard part, right? You're going to like the Born-Haber diagram way better because the Born-Haber diagram just bypasses all of this garbage, right? But I want to show you that this works using Hess's law, right? It's the only time I'm going to do this for you. And in the next video, we'll do Born-Haber diagrams, okay? So remember, we got 2 pathways. Let's do it for silver oxide specifically. Path 1, you just form 1 mole of that solid from its elements in their standard states, and that's the standard heat of formation, right? You can read from a table. Path 2, we're going to get from the elements in their standard states to the ions in the gas phase and then combine them using the lattice energy, and that will leave us with 1 mole of the solid, of the ionic solid, right? Okay, so ready? So here's the steps for it. Take a look at your metal and your nonmetal. Are they in the gas phase or not? Oxygen is, so I don't have to worry about it. Silver is not. So step 1, get all your elements into the gas phase. So I got to take those 2 moles of silver solid, convert them to 2 moles of silver in the gas phase. That would be the molar heat of sublimation times 2, because there's 2 moles, because that'll be kilojoules per mole times 2 moles. Good to go? Then, and we don't have to worry about the oxygens already in the gas phase. Then step 2, take your metal, convert it to the cation. So we need to remove electrons. So let's take those 2 moles of silver in the gas phase, remove 1 electron from each, so I'm going to get 2 electrons and 2 moles of silver ions in the gas phase. That would be the first ionization energy of silver times 2. That'll be kilojoules per mole times 2. We'll put numbers to it in the next scenario. I don't know if, yeah, we'll do Born-Haber diagrams in the next video. All right, so we now have 2 moles of silver in the gas phase. That's what we want for the lattice energy, right? All right, step 3. If your nonmetal is polyatomic, split the bond. So oxygen is a double bond. So we're going to take that half a mole of oxygen, take the 1/2 times 2 gives us 1. But we need to break that using the bond energy, right? And that's that 498 kilojoules per mole. So we'll take that bond energy, 498 kilojoules per mole, times 1/2 of a mole of oxygen. Hey, that leaves us with 1 oxygen atom in the gas phase. Okay. Now we need to, in step 4, take that now monatomic nonmetal element in the gas phase and add enough electrons to get to the correct charge. Now, the oxide ion is a -2. Right? So we have to add electrons twice. So here's the first one. So we take that oxygen atom in the gas phase, add an electron, and we get the O- in the gas phase. That's the electron affinity of oxygen times 1 mole, right? And then we take that O-, add a second electron to create O2-. That's the second electron affinity times 1. And remember, the first and second electron affinities are not the same. So take a look at, that's ionization energy. So here's oxygen. So the first one is negative 141 kilojoules per mole. The second one is positive 744. It's a lot harder to put that second electron in there, isn't it? So, and if that was -3, I'd do that in another step. Okay, so when you have charges of +2s, +3s, -2s, -3s, there's a whole lot of steps in here. This can get bulky. All right, so now I've got my metal cation in the gas phase, my nonmetal anion in the gas phase. So I take my 2 moles of silver ions in the gas phase, combine that with my 1 mole of oxide in 2- charge in the gas phase, and I get exactly 1 mole of silver oxide solid, right? That's your lattice energy. Well, I formed Ag2. The end result is Ag2O, Ag2O. So the sum, if I add all these equations, that value should equal that value. The sum total of path 2 should equal the total of path 1. That's Hess's law. So let's add all this together. Ready? Let's start crossing out. Ha ha ha, this is the best part. Anything you see on the left that's the same on the right, we can cancel out. Right? So do you see 2 moles of silver solid on the right-hand side anywhere? Nope, I don't. So that does not cancel out. Let's take a look. We've got 2 moles of silver in the gas phase on the right, 2 moles of silver on the gas phase on the left. Bye-bye. Bye-bye. Goes bye-bye. I see 2 moles of silver ions on the gas phase on the right. 2 moles of silver in the gas phase on the left. Boop, boop. Bye-bye. Gone, gone. I see 2 moles of electrons on the right. 1 + 1 is 2 moles of electrons on the left. 1 and a 2 on the left, 2 on the right. Electrons go bye-bye. When we're all done, we should end up with that equation, right? That's Hess's law. It's just an indirect way to do that. I've got 1/2 mole of diatomic oxygen gas on the left. I don't see that on the right, so that does not cancel out. That's a good thing because it better end up there. I got 1 mole of monatomic oxygen gas on the right, 1 mole of monatomic oxygen gas on the left. Goodbye, my friends. That's history. I see 1 mole of the -1 oxygen in the gas phase on the right, 1 mole of the -1 oxygen in the gas phase on the left. Bye-bye. That goes bye-bye. I see 1 mole of the O2 oxide ion, O2- ion on the right, and 1 mole of O2- on the left, so that cancels that. I see 1 mole of Ag2O solid on the right, doesn't cancel out, so those are the only things left after we add this all together now. So what are we going to get? We've got the 2 moles of silver solid. Gone, 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 gone. Oh, we've got 1/2 mole. We're really just looking on the left-hand side. So left-hand side of the arrow, there, gone, there, gone, 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 gone. So those are the only things left on the left-hand side. Let's look on the right-hand side. Gone, 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 gone. The only thing left is the Ag2O solid. Would you agree that that equation matches that equation? I hope you agree, which means the sum of that plus that plus that plus that plus that plus that has to equal that. Path 1 equals path 2. Let's write that. We just created a mathematical equation using Hess's law. You can do this for any ionic solid. If the process is exactly the same, sometimes you'll skip step 3 if it's not a diatomic nonmetal, which is easier, right? But the setup's exactly the same every time. And then you just got to look up these values, right? I'll give you that. Those you can look up on the table. Those you can look up on the table. Those you can look up on the table. We're solving for lattice energy. This you can look up on the table. Let's put the equation together on the next board. Once you get this stuff's, it's fun in a very morbid, nerdy way. All right, let's polish it off. I'm not going to put numbers to it. We'll do that when we do the Born-Haber diagram in the next video. So we can set up an equation for using the Born-Haber cycle for any ionic solid, right? They're unique to each solid. You ready? We proved from Hess's law, we proved it, that path 1 forming the solid from the elements in the standard states equals path 2 forming the solid from the elements in their standard states, all the way converting them to the ions in the gas phase and then using lattice energy, that 5-step process. So from path 1, that's just the standard heat of formation. Easy peasy. That should equal all of path 2, those 5 steps added together, which was from step 1, molar heat of sublimation times 2 for silver oxide. For step 2, we ionized the silver, right? So 2 times the ionization energy. Step 3, we had to break the oxygen in half, the diatomic oxygen. Since we had a half a mole, we had to times it by half. Then we had to add electrons to make it a -2 charge. So we had 1 mole of oxygen gas, monatomic, times the EA1, adding the first electron to get O-. Then we had to do that again with the second electron affinity to get it from O- to O2-. So those two combined were step 4, going from O in the gas phase to O2- in the gas phase in 2 steps. And then we took the metal cation, non-metal anions in the gas phase, combined them together. Step 5, that was lattice energy. So all of this is path 2. Path 1 equals path 2. You now have your equation. The only difference will be the coefficients might change. You might have to add vaporization if you have a liquid. You might not need the bond energy if it's not a diatomic, like chlorine or something like that. Now, most scenarios are going to be solving for the lattice energy. But if I gave you that, I could have you solve for any one of these, couldn't I? Right? As long as I give you values or tables with everything except one, you can solve for that one. But most commonly, we can look that up. That's provided, look that up, look that up, look that up, look that up on tables, which I'll give you on quizzes and tests, and we're going to solve for the lattice energy. Okay? So if we want to isolate the lattice energy, well, lattice energy will just equal the molar heat, the standard heat formation, right? And then subtract this, and this to isolate lattice energy. So we take the standard heat of formation minus 2 times the molar heat of sublimation, minus 2 times the first ionization energy of silver, minus half the bonding energy for the diatomic oxygen, minus 1 mole times the first electron affinity for oxygen, minus 1 mole of the second electron affinity for oxygen. Look that up, 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 look that up. You just solve for lattice energy. Hey, let's do that in the next video, but I'm going to summarize all of this mess into a beautiful, concise Born-Haber diagram. You're going to love Born-Haber diagrams.